Hi guys, in today's class we'll be talking about force on the current carrying conductor. Now force on the current carrying conductor, we actually had this idea from Lorentz and Faraday's law, where it was observed that when a material is placed in a magnetic field, there will definitely be a change of flux. And when there's a change of flux, then that means that there is a voltage across its terminal and there is a current flowing through it. Now let's say you have a magnetic field like this. And in this magnetic field, you have a similar one like this too. It happens to be that there are magnetic fields here. That was a magnet and these are magnetic fields. So right here, we can simply call these north and this is south. But there's something that is key. You observe that if we have a material in between, let's say you have a rod, a cylindrical material, in between the magnetic field. Then because this lies here, then they will be detected that there's a current flowing through this material. So from this point to this point, we can see this as the length of the material. L. Now, don't forget there's a current flowing through. Then there is a flux density due to the magnetic field. That gives you B. So B is measured in Tesla, usually symbolized as T. Well, that's probably the unit of B, symbolized as B. The unit is Tesla, which is shortened to T. I is the current. And of course, current is measured in what? Amperage, amperes. And L is the length of the material. We know vividly that these are even the standard measurements. The length, which is in what? Meters. So whenever, this is a salient point of this, whenever you see the material or the cylindrical material perpendicular to the magnetic field, then it is known that there is a situation of 90 degrees formed there. So in this way, generally or basically, we can see this as F equals BIL. I am just giving this based on the fact that I'm not considering the angle in this case. But this can only happen when you have a 90-degree situation. Because normally, this is meant to be F equals to BIL sine 90. Because of the perpendicular state. And of course, when you check sine 90, that's 1. But if this material is parallel to the field, when I mean the material is parallel to the field, I'm saying this as this. So this is parallel to the magnetic field. I will be seeing this 90 as what? 0. So this F equals BIL sine 0. When you use your calculator, sine 0 is what? 0. Of course, 0 multiplied by everything here gives you 0. So your force is 0. So you can just give a short note and state that when 0 newtons, you can say whenever the conductor is parallel to the magnetic field, then we're having 0 newtons. That the force generated is 0. But whenever the conductor is perpendicular to the magnetic field, then we have a 90-degree situation. F equals BIL still stands because 90 is what? You have sine 90 as what? 1. Let's take a good question. I have a question. A current of 3 amps flows through a wire. Obviously, I'll come here. If you want to draw, it's fine. So I have another one. This is the 2D shape of it, not like 3D. These are the magnetic lines. Magnetic lines of flux. So let's say this is my current carrying conductor. Well, that's not 90 degree actually. I'm going to symbolize, yes, this should be a 90 degree situation. So if I have this, what comes to mind is, of course, in physics, you write out your parameters. Your current, I, equals 3 amps. Now, I know that I have 3 to be 3 amps, which is easy. I state other parameters. Then from here, your length is what? 0.2 meters. Then your magnetic flux, which is symbolized by B, measured in Tesla, 0.1. Now, because this is perpendicular, I'll be using F equals what? BIL sin 90. Don't forget that your B is what? 0.1 Tesla. Your current is what? 3 amps. Your length is what? 0.2 meters. Sin what? 90. I can just multiply my sin 90 here by 1 because I know that sin 90 gives me what? 1. So if you input that, that gives you 0.1 times 3 times 0.20. And at the end of the day, you're having a force of what? 0.06 newtons. 0.10 times 3 amps times 0.20 lengths. So that still gives you what? 0.06 newtons. Thank you so much, guys. I appreciate you deeply. I'll see you in my next video. Bye.